Welcome back. In this set of videos, we're going to be looking at graphing rational functions. In our last set of videos, we looked at graphing reciprocal functions, which are one specific type of rational function. In these videos, we are going to be looking at general rational functions, which are ratios of two polynomials. So we'll define our numerator as a of x, a polynomial having terms a sub n times x to the n, plus a sub n minus 1 times x to the n minus 1, all the way down to a sub 0. And b of x is b sub m times x to the m plus b sub m minus 1 times x to the m minus 1 plus terms all the way down to b sub 0, where my a sub n and a sub n minus 1 and b sub m, those are all coefficients. So I have a leading term in the numerator of a sub n times x to the n and a leading term in the denominator of b sub m times x to the n. So if that's my definition of a rational function, we have a couple key things that we need to consider. Our first is, what are domain restrictions of these functions? What's the possible domain? And then how do those manifest themselves in our graphs? So when we look at domain restrictions of rational functions, we're really looking at our issue being division by 0. We can't divide any number by 0. That's an illegal operation in math. So anything that makes my denominator equal to 0 is going to be a problem. In order to find those, we're going to fully factor our equations. So we want this numerator and denominator both fully factored. Right now, the denominator is our key thing. Whatever values make our denominator equal to 0 are domain restrictions. Once we fully factor and we get our list of domain restrictions, we are going to simplify. And when we simplify, we come up to this question of what if a factor cancels out? So what happens if a factor cancels out? So we're going to look at an example here to figure out what if a factor cancels out. So here's my example. I have x squared minus 1 over x plus 1. So my first thing is I want to state my domain restrictions. My domain restrictions are the denominator cannot be equal to 0. So I'm using this. So x plus 1 can't be equal to 0, so x cannot be equal to negative 1. My denominator is fully factored. But I want to fully factor my numerator as well. So I have this domain restriction. The denominator can't be equal to 0. So x squared minus 1, that's the difference of squares. So that is going to factor to be x plus 1 times x minus 1. And what I notice when I'm simplifying is that I have a common term or a common factor in the numerator and denominator that I can cancel out. And I'm left with just x minus 1. So my original equation is x squared minus 1 over x plus 1. And my simplified is just x minus 1. But I had this original domain restriction of x can't be equal to negative 1. It disappeared. What's going to happen to my graph? I'm going to start by just picking some x values. So like negative 2, negative 1, 0, 1, and 2. Just as a couple values that I'm going to plug in and check. I've got a calculator here just in case I need it. Probably won't need it because these are simple numbers, but so I've got negative 2 squared minus 1 over negative 2 plus 1. That is 4 minus 1 over negative 1. That's 3 over negative 1, or negative 3. If I plug in negative 2 to my simplified equation, I get negative 2 minus 1 is negative 3. So you'll notice that at negative 2, I get the same value in each. Let's try 2. 2 squared minus 1 over 2 plus 1 gives me 4 minus 1 over 3. That's 3 over 3, or 1. If I plug 2 into this equation, 2 minus 1 is 1. I again get the same value. So I'm going to put a smiley face because these are the same value. Let's check 1. 1 squared minus 1 over 1 minus over 1 plus 1. So 1 squared is, so this becomes 1 minus 1 over 2. That is just 0. And if I plug 1 in to my simplified, I also get 0. Let's check 0. 0 squared minus 1 over 0 plus 1, that's going to give me negative 1. 0 minus 1 is negative 1. And if I check negative 1, this was my domain restriction. So if I check my domain restriction in my original problem, I get negative 1 squared minus 1 over 1 minus 1. So that gives me 1 minus 1 over 1 minus 1, which is 0 over 0, which is not possible. This means that my graph is undefined at this point. If I plug negative 1 in over here, I get negative 2. So at this point, at x equals negative 1, this is the only point where my original function and my simplified function do not agree. So what happens when I graph my function is my function, my original function is exactly the same as my simplified function, with the exception of my domain restriction. At this domain restriction of x equals negative 1, I'm going to have an open circle. My function does not exist only at that exact point. But 0, negative 1, all these other points on here, my graph exists. So this is the point negative 1, negative 2, where my graph does not exist. So we end up getting a hole. And the definition of a hole is that if after simplifying a domain restriction no longer appears in the function, that restriction represents a hole in the graph, or a point that does not exist on the graph. My graph is exactly the same as this, so this rational function turns into a line with a hole. In our next video, we'll look at some examples of finding vertical asymptotes and holes.